Welcome to queenon7.com. Please like and share my videos. Today we're going to learn about the second part of the acid, base and buffers. We will look at the pH of the weak acids and the strong base. Weak acid does not dissociate completely in the aqueous solution, whereas strong bases, they completely dissociate into OH negative ion and obviously a metal positive ion. Now, one more thing you need to remember, the initial concentration of the acid will be equal to the concentration at equilibrium. The reason is it only dissociates a very tiny bit. That's why we assume that the initial concentration will be equal to the final equilibrium concentration. Now, you need to remember one thing, that all these acids like HCl, HNO3, H2SO4, H3PO4, all of them, they are strong acids, and their concentration of the acid will actually be the same for the ions they have made because they completely dissociate. But if you talk about the weak acid, the identification most likely carboxylic acids like ethanoic acid, you have methanoic acid, propanoic acid. Wherever you see COOH, they are most likely the one we use for the weak acid examples. Now, in this example, we will look at the weak acids. The H positive ion and the negative part of the acid, their concentration also be the same. So whatever you are producing in terms of H positive ion and the negative part of the acid, they both have the same concentration because they actually are going to dissociate in the same amount. So same moles will be produced. Now let's take an example of one of the weak acid, which is ethanoic acid. First of all, we need to write down the expression of Ka. So if you say Ka, which is equal to the concentration of the products in ethanoic acid, it will be CH3 COO negative ion, and then you have H positive ion. You divide it by the concentration of ethanoic acid, which is CH3 COOH. This will be obviously be the same. So if they have given you this as the initial concentration, it will be the same even after the equilibrium. This is because this is the equilibrium expression. Now, if you look at the concentration of the ethanoate ion and H positive ion, they both are equal as well. So you can rearrange that, and you can actually say it's actually H positive ion square, and you will write down CH3 COOH as it is. Now, to rearrange the equation, our primary focus is to find out the pH. In the previous video, I have said that if you want to find out the pH, your focus should be I'm going to get to H positive ion concentration. Based on this, you can rearrange the equation, which will be H positive ion square is equal to Ka times the ethanoic acid concentration. Once you find out the value from here, which is obviously 1.7, 10 raised power minus 5, and you have to times it by the 0.1 molar solution, which is 0.01 mole, it will come here as 4.12. And then you can solve this by taking a square root. So if I remove this and if I write this expression here, H positive ion concentration is equal to 1.7 10 raised power minus 5 and 0.01, and I take a square root of this, that will give you the concentration of H positive ion. And after that, you can use this as for writing down the pH, which will be pH is equal to minus log of H positive ion. When you're going to solve all this equation by taking a square root and then the minus log of whatever the answer comes from here, it should come equal to 3.38. A shortcut for you to remember that whether your answer is correct or not, whatever you're going to get here, whatever the value you'll get for H positive ion, it will have something like 4.12 10 raised power minus 4. I think something like that you're going to get the answer from this equation. Now the minus 4, your pH should be equal to -4 or less than -4. It should not be less than 3. So this is a shortcut to remember. Most likely your answer will be 3.8, 3.7, 3.5. It's a shortcut to remember. It's not accurate, but that's how you can check it. Whatever the 10 raised to the power, your pH either is equal or less than that, and this is how you can check your answer is correct in exams. Let's take about the strong bases. Strong bases are the ones which are going to completely dissociate into the positive and the OH ion. So it's more likely POH we normally look at when we try to look at the power of hydroxide ion. Now, if you want to find out the pH of a base where you cannot see H positive ion at all, it is then you're going to use the water dissociation constant, which is Kw. So the Kw is equal to the product of obviously Na positive ion concentration and OH negative ion concentration, and you divide it by the NaOH. That's the general, this is the general expression for Ka. But if you use Kw, which is H positive ion concentration and OH negative ion concentration, it is a lot easier for us to actually calculate the pH using Kw. Kw is actually equal to 1 into 10 to the power minus 14 at 25 degrees centigrade. H positive ion concentration is not given, so we are actually trying to find out H positive ion concentration. OH ion concentration is given. Because it's a strong base, so whatever the concentration of the base, it will produce the same amount of or same moles of the OH ion in the solution. So the concentration of the OH ion is exactly equal to the concentration of your base at the start, because it's a strong base. So you will put 0.1 mole per dm cube over there. Now when you rearrange the equation, the H positive ion concentration will be equal to 1 into 10 to the power minus 14 divided by 0.1, so it will be 1 into 10 to the power minus 13. Now if I take the pH of this, it is minus log of 1 to 10 to the power minus 13, that will give you me 13. So 13 is a very, very strong base. So pH of a base, especially like NaOH and KOH, they have a strong pH, nearly 13 or 14. That tells you this NaOH is a very, very strong base. Thank you very much for watching my video. I will be uploading some video about the buffers in the next video. Thank you.